All right, so the next thing is the non-parametric t-test. So we're going to start to run these when the t-test violates the assumption of normality. If you don't want to do a non-parametric, there are some other things that you could try with the t-test. Obviously, you can try a larger sample. The larger sample, or the central theorem, seems to say that as your sample gets larger, the potential for normality increases. But again, that's probably limited by economics and how much money do you want to spend when you're sampling. You can also transform your data like we talked about before with the 3 different types of transformation. You can conduct a trimmed mean. A trimmed mean is if you have a substantial amount of outliers, you could take 5% of the data or 2.5% of the data off either side of your data set. So you take your data, find your midpoint, and take off 2.5% of the data points on one end and 2.5% on the other end, and then rerun your data to find out whether it's normal or not. So there is some other ways to handle that. And then, of course, you can always just flat out run the non-parametric test. The reason the non-parametric tests are a little bit nicer because you have a few fewer assumptions. And one of those fewer assumptions is flat out the data does not have to be normal. There are 3 different types of non-parametric t-tests that we're going to talk about. 2 are associated with the independent t-test, and 1 is associated with the dependent t-test. What I've got for you here is a nice little poem. I don't remember who wrote it, but I don't know. This is how statisticians find humor in the world. So you may or may not find it funny. I found it funny. All right, non-parametric test. Generally what they're going to rank the data. Doesn't matter which type of test you're going to run, they're going to end up ranking the data. Lowest score gets 1, next highest score gets a 2, tied ranks get the same rank. Generally it's the average of the 2 ranks, and then we're going to carry out the analysis on the ranks instead of on the actual data, which is why normality does not matter. So the way they're going to do is they're going to actually add up the ranks for 2 different groups and generally take the lowest of those ranks and use that as the test statistic to be able to compare the 2 groups. So we're going to go over a couple examples of these. All right, so the problem with this is when you rank the data, you do lose a lot of information about the descriptive statistics. Obviously, that can create some problems. Non-parametric tests are less powerful than parametric tests, and there's a lot of folks out there that say this quite frequently. If there's a genuine effect in the data, the parametric test is more likely to detect it, but there's one problem with that. That only happens if the assumptions are met with the parametric test. So if you do not have normal data, your non-parametric tests are actually more powerful than the parametric test. So when the data is not normal, our type 1 error rate increases, and you're not exactly sure what the distribution is or what the type 1 error rate is. Therefore, you can't really determine the power. And that makes non-parametric tests under non-normality much more powerful. All right, we're going to start with the Wilcoxon rank sum and the Mann-Whitney, generally testing the difference between 2 conditions with different participants. That's why it is the independent t-test non-parametric version. Both of the tests are actually very similar, have slightly different test statistics. Wilcoxon rank sum uses a W sub S test statistic, which is the sum of the ranks in the group that has the least data. If you have equal ranks, you just take the sum of the smaller ranks. Again, SPSS is going to do a lot of this information for you. However, you do have to do some things. So we're going to go over what these things are that you have to do. All right, we're going to have a traffic engineer that's collecting data on the effects of drinking and driving. Testing 20 drivers. 10 were given 1 drink, and 10 were allowed to drink as much as they desired. And then they measured the lane deviation, or the amount of their ability to keep their lane, 3 hours after the test began, and again the following morning. So here is our data. So we have 1 drink versus 2 drink. 1 drink is 1 drink, and 2 is as many drinks as possible. And then the lane deviation for the morning test and the lane deviation for the 3-hour test is shown. All right, so the process is you arrange the data in ascending order. All right, so we're going to look at the 3-hour data. Our data here is arranged in ascending order from 3 to 39. And then we're going to start at the lowest and assign a rank. And this is just a potential rank. So you're going to rank these in order. We had 20 people, so we should have ranks from 1 to 20, which is what we do. Now we're going to take a look at this and we're going to say, all right, well, who has similar data points? We have a tie here between 6 and 6. And we have a 3-way tie at 35. All right, so we look at 6 and 6. We say 3 plus 4 divided by 2 is 3.5. So 3.5 is our final rank. And then we take 16 plus 17 plus 18 for the ties of 35. Divide that by 3, and they all get the rank of 17. Everybody else, the potential rank, just goes over into their final rank. All right, then what you do is you add up the ranks for the 2 groups. So we had 59, had no limit, right? So we have all of our data here, no limit and 1 drink. We're going to add up our ranks under the no limit and add up our ranks for the 1 drink. And 59 for one, 151 for the other. So our W sub S is a smaller of that, so it is 59. And then we can calculate our mean, standard error, and the z-score. So pretty easy calculations. And then the z-values are larger than the absolute value. The test is significant. So we have a z-value of 3.48, which means the test is significant at a 95% confidence level. So that's the Wilcoxon test. The Mann-Whitney test uses everything else is the same, except it has its own special test statistic instead of the WS. It's the U, and it still follows the same as compared to the 1.96. All right, so how do you do this in SPSS? First thing that you would have to do is you're going to look at your data. So we have some non-normal data. Non-normal data for 3 hours no limit, and non-normal data for 1 drink in the morning. So our data is non-normal. Do we have homogeneous variances based upon the mean? Yes, we do have homogeneous variances. So it does meet that assumption. Again, go to SPSS, you can see how to do that. There's a whole bunch of other tests also when you start to get into SPSS. The Kamal-Smirnov Z, this is not the same test as the normality test. It's very similar to the Mann-Whitney, and it's actually better if the samples are less than 25 per group. You could also play around with... All right, so let's go ahead and look at the example output. So looking at the Mann-Whitney test, we did the Wilcoxon manually, so we're just going to look at the Mann-Whitney test and SPSS. The group with the lowest mean rank is the group with the lowest number of data points. All right, so the lowest mean rank, 5.9, is one with the lowest number of data points. So this is just kind of useful information. So now you kind of understand what that means. When we look at that, we can kind of look at those two values and get an idea. So this is simply just useful for interpretation. Because when you think of the way we ranked everything, lowest lane deviation, we started out ranks at 1, and then we went up to approximately 20. So people that had the lowest lane deviations were going to run up down here. And high lane deviations meant they were having significant lane deviations up here. So those that had the sum of the low numbers are the ones that actually had better lane deviation. They were swerving less. All right, the test statistic actually shows that both tests are significant. So drinking 1 drink or as many as desired does not impact lane position the morning after drinking. However, it does impact it after only 3 hours. So let's go through that one more time. So the significant value for either the asymptotic or exact significance for the morning test is not significant. Which means right, drinking 1 or as many drinks as you want doesn't impact how you drive in the morning. However, drinking 1 or as many as you want does impact after 3 hours. And that again is at a 95% level of significance. All right, so why do we have 2 significant values? The asymptotic and the exact. When sample sizes are very small, the exact is generally more accurate. Right? So when we have small samples, we're going to want to look at the exact significance instead of the asymptotic. If you had a very large sample set, 10, 20 is not a very large sample, you would want to go ahead and look at your asymptotic significance. All right, so now we know that drinking 1 or as many drinks after 3 hours does impact lane deviation. So let's go back and look at this. And now we need to be able to interpret the mean rank of this data. So after 3 hours, After 3 hours, the group drinking one drink had higher lane deviations than those without a limit. So maybe the sample was taken at Ohio University, and the people at Ohio University can drink and drive better than others. So this is not good if you're hoping that drinking and driving is not good. Again, this test is not representative of real data, so please don't try this at home. But that is exactly what the data is saying. It's saying that if you drink a ton, you're going to swerve less than if you just drink one drink. Interesting output. All right, so let's go ahead and move on to calculate